It is accumulation of liquids in the liner due to reduced fluid velocity, and how understanding of liquid loading process helps in formulating a more sustainable solution. I'm Mustafa Amir, Senior Petroleum Engineer at Bapitco. We will... It's not responding. It's not, I feel like it's quite slow.
Yes. So I switched the slide. We now see the agenda.
Yes. We will discuss liquid loading in theory, and then case study of an implemented project where we navigate from design and workflows to operations and results. Then we will sum up. Liquid loading of a gas well is the inability of the produced gas to produce the entrained liquid from the wellbore. Tana discovered that liquid loading could be predicted by a droplet model that illustrates when droplets move up or down depending on the gas velocity relative to a critical velocity. The balance between the drag and the gravitational forces determine whether the droplets are going to accumulate in the well or not. Below Tana critical velocity, liquids fall back down the well and forms a liquid column at the bottom of the well, reducing drawdown until the well dies. The solution is to tackle the largest ID section of the well where fluid velocity is small, usually the liner. It's common to use the VLP to diagnose liquid loading, where flow rates to the left of the minima, the red area, is usually dominated by hydrostatic effects, while flow rates in the green area are stable and are dominated by frictions. In practice, the critical velocity is generally defined as the minimum gas velocity in the production tubing required to produce with low probability of liquid loading. If we come back to Tana's approach, the droplets accumulate in the large ID section, but for his approach to be valid, a bubble flow should be taking place in the liner. And as we see from the flow diagram here, a bubble flow needs to have a very small gas velocity. It can happen at the very far left end of the VLP, but what is really happening below the minima, the VLP minima? What is happening in this liquid loading region described by Tana? What do we expect to see in terms of liquid loading if we shut in an intermittent gas well? What is the liquid column is going to be? Will we see a liquid column that's equivalent to the formation drawdown, or it's not going to be equivalent to the formation drawdown? In many cases, we don't get the size of liquid column that we expect to balance the formation drawdown when we shut in the wells for cycles. Then what is going on in the wells? We use PT function in Pipesim, where we investigate what happens to the gradient across a well as we drop below the VLP minima. The modeling was performed over a well with 7-inch liner and 5-inch completions. At point A in the friction-dominated region that's stable, some evidence of liquid holdup happens in the liner due to the change in gradient. If we move to point B in the friction-dominated region, frictions reduce because of reduction in velocity, but we see more pressure drop in the liner. As we move to point C in the minima, we see higher pressure drops in the liner and the frictions in the tubing reduce. Let's see what happens if we go to the hydrostatic dominated region. We go further down with rate. The tubing, the pressure drop in the tubing and the liner both increase. This is a fundamental shift in the perception of liquid loading. Liquid loading then in a gas well, it's increased liquid phase holdup over the entire well and the tubing and in the liner due to phase slippage at lower gas velocities. Once a well is producing below its minimum critical rate, all liquid influx is held up in the wellbore and the form of agitated column. And this column doesn't always form at the bottom, but instead it may happen in the upper portion of the wellbore, according to Coleman 1991. So we don't need to focus on increasing the velocity in the liner area. Instead, we need to increase velocity in the tubing itself. Our field is onshore gas field in the depletion phase, with low rate of success in some of the new wells as we see here. The majority of production coming from new wells. The area shaded with red contains wells that are described as old wells with 5-inch completions. Around 10 of them are suffering from liquid loading issues. By the way, the chart represents the distribution of production data per well over the past 2 years. Our champion for today is the one highlighted in red. As we got from the literature review we went through, that we need to eliminate the liquid drop out in the tubing. We need to increase the flow velocity in the tubing. We need to have a smaller tubing in the well. But what are the possible options? We can replace the existing completion. We can produce the wells on cycles. When the well dies, vent the gas to the atmosphere and send the liquids to the sand, which is not an environmentally friendly option. And install velocity string using a snubbing unit, or run 2-inch tubing, 2-inch coil tubing. However, all of these options have disadvantages. The major disadvantages related to health and safety, overriding the subsurface safety valve, not complying with the well integrity standard, killing the reservoir during operation with its considerable loss of productivity. But what if we can run velocity string without killing while complying with well integrity standards? Then the best option will provide the best performance is to insert velocity string completion without killing, while having operable surface control subsurface safety valve, without using snubbing unit that's not available in the country, ending the cyclic operation to prevent pollution and emissions from the well, and all this should come at acceptable cost. Liquid loading velocity ratio is one of the main design parameters that we will investigate as well later. It means the minimum lift velocity divided by the fluid velocity. If the liquid loading velocity ratio is greater than 1, then the well is operating in the hydrostatic dominated region and liquid loading will happen. But if the liquid loading velocity ratio, as we see in the green shaded area, is less than 1, then we are in the friction dominated region and the VLP. We are in the more stable region with low chances of liquid loading. The surveillance was directed toward investigating the liquid loading wells at a customized way through in-house development code that integrates production and reservoir data. The aim of the tool was to provide customized production performance analysis on well level for all wells in the field, around 80 wells. In the other direction, we combined production, reservoir, well integrity, and completion data in a Power BI, Microsoft Power BI model to gain more insightful analytics of the integrity failure history, integrity status, depletion, well potential, clearance, hence maximizing the gain by tackling well integrity issues with running velocity string, and also avoid operation complications. The goal was to select the best candidates while maximizing gains relying on the company datasets. The selected candidates from Python analysis and then from the linked databases in Microsoft Power BI goes to Pipesim to calculate PT profiles, liquid loading velocity ratio, and estimate the expected gain. The process keeps going and coming between the two to select the best candidates and score them as well. On the surface network level, Pipesim was used with the help of Schlumberger team to model the surface network and make sure that production gains from the intermittent wells will not be constrained by the network capacity or high pressure wells. Investigating the liquid loading velocity ratio we introduced earlier for different tubing sizes at different pressure scenarios. As we see, the existing 5-inch tubing allows the well to always produce under liquid loading conditions, while the 2-inch and the 278 completions have liquid loading velocity ratios less than 1 and keep the well in the friction dominated region that's stable. We selected the 278 completion as it provides higher operational rate and easier future intervention. To run a velocity string without killing and without using snubbing units, the operation was as follows. Rigorous inspection of the existing 5-inch completion and setting an isolation packer with a surge disc. And then a workover rig runs the 278 completion inside the existing 5-inch completions and set another packer below the surface control subsurface safety valve. And then rigorous coil tubing, kick the trapped brine and break the disc to kick the well to start. In terms of production performance, the production assessment considered 5 months of production before and after running the velocity string. The orange curves represent the performance after running the velocity string. As we see, the production performance profile is more stable compared to the fluctuating performance that we used to get before. And in the violin plots here, the data are more scattered before with lower mean, but currently it shows that the data are more, the range of data is shorter with higher mean. The project KPIs were on 3 main levels. The economic level, the cost of using workover rig to install the 278 completion is 10% of the snubbing unit, and the project payback time was around from 5 to 6 weeks. On production performance level, in relative terms, the project helped to increase the cumulative condensate production of the well over 5 months by 4 folds, while increasing gas rate by 1.5 folds. On the environmental level, compared to cycling operation, the monthly reduced greenhouse gas emissions are equivalent to 4.4 million miles of average passenger vehicle emissions. And also we managed to achieve operation efficiency by reducing workload on production operation team, compliance with our well integrity standard, and we secured the well from killing. In conclusion, now we have our own way of treating intermittent gas wells that is less expensive and doesn't require killing, and allows for compliance with our well integrity standard. It's a very big problem in Egypt, as we even see from our colleagues in Apokir Petroleum. They were talking about liquid loading and intermittent gas wells as well. The increased head from changing flow regimes in the tubing governs liquid loading, not just the condensation in the liner section, in the big cross-section area. Reducing emissions from upstream operation is feasible, and it could be accompanied by economic gains. Even though liquid loading is a dynamic process, Pipesim provided a very useful clue to estimate the liquid loading velocity ratio that it showed success. Finally, I would like to thank Babitco management team for allowing to share the work, and Babitco technical team for the enormous efforts they have put in this project, and also Schlumberger and Egypt technical team for their knowledge and their cooperation. Thank you.
Thanks a lot, Mustafa. That was very interesting and also very fast. So I think we have time for some questions. Please post questions in the mural. I have a question for you while we look at that. How long do you see that velocity strings will be sufficient before you have to go into using some type of lift method to get the liquid out?
There was a big assessment project I've done in the company, comparing like using compression units, using plunger lifts and other stuff. But most of it ended up to be very expensive. Even the assessment was done during the high oil price era, 2013 and 2014.
So, and you now use the velocity strings for all your gas wells?
No, we have done this on 3 wells. 2 of them showed great success. But the company managed to run on priorities, especially during these times.
Mm-hmm. Very good. No, very nice work. Yeah. There's a couple of questions on the mural, and you can also unmute if you have questions, because we have still some time. Can liquid loading predictions method used in Olga be used in Pipesim?
Actually, I didn't use Olga because we don't have the access to it. That's why we were forced to use Pipesim. We squeezed it to get the maximum out of it.
Yeah, I can also maybe say that normally, as you say, liquid loading can be done with the Turner equations. We do some liquid loading in Olga, but that's typically when you want to also capture the near wellbore. And the liquid method, especially when it's shut down, is also gets into a transient scenario. But Pipesim does an excellent work on liquid loading. Any more questions? I think keep posting, or if the Pipesim team probably has some questions to ask.
So may I ask a question? Because
Yes,
I don't have access to the mural. That's a problem. So excellent presentation, Mustafa. I really enjoyed it. It's a question not necessarily related to simulation, but to the solution you approach. You install the velocity string using two packers, up and down. So you basically isolated the annular space between the tubing and the velocity string. So
yes.
do you have any sustained annulus pressure in that space? Any concerns in that area?
No.
No,
because
you don't.
it's already isolated. But what we have done during the operation, guys, what they have done during the operation is that we tested it with, I think, 1,000 psi on the surface pressure, 15 minutes, and it was okay. And even we proposed it for fixing integrity failure in existing completion, pinhole existing completion in the area between the packer and the subsurface safety valve.
Okay, all right. Because it always might be a problem with the packer leaking and building up some pressure in that space, and then you might be having some I don't know, some integrity issues.
A good thing is like these wells, the reservoir pressure is quite low. The reservoir depth is 4,000 meters, and the reservoir pressure is like 1,400, 1,500 psi.
All right, so not a big concern.
So if you allow me, this is Ahmed. I'd like to say that I'm really impressed with the work, Mustafa. You know, since I am the Pipesim product champion, I really have to, really congratulate you for, as you said, push the envelope in Pipesim. You have really, you have really reached into a point where I never imagined that Pipesim can be used for, but this is really a great job. And I'm always thrilled when I see our users dig into Pipesim and try to extract value out of the engine, and this is amazing, and really thank you, and good job, and wish to continue similar.
Thank you so much, Ahmed. I'm a big follower for you on LinkedIn, and that's a big word to say for the team who have done the work. Thank you so much.
No, great job.
Mustafa.
Hello?
Mustafa. I can't join the mural. I have a question. What criteria do you use or you base on to choose the wells?
Choosing the wells was depending on the main thing was the operational risk. So we chose wells that doesn't have problems in the existing 5-inch completion at the area below the subsurface safety valve and at the end of the tubing. That was one thing. The second thing was the potential. If we insert the 278 completion, are we going to have good rate or not? Are we going to achieve the liquid loading velocity ratio that's less than 1 or not? And also was the rate of the logarithmic depletion of pressure, of wellhead pressure.
Okay, thank you.
Any more questions? We have time for one or two more questions to Mustafa.